In this video lecture, we will be taking a look at some alkyne reactions. To follow along, you'll want to look at your alkene-alkyne reactions handout, pages 9 and 10. In this discussion, we'll be looking at several different kinds of reactions. The first will be hydrohalogenation of alkynes, where we'll take a look at reaction of an alkyne with HX, like HBr. We'll take a look at the reaction that occurs in both a Markovnikov and an anti-Markovnikov fashion. Then we'll move into halogenation of an alkyne. That's reaction with X2 or Br2. Then we'll look at different kinds of reduction reactions. You can reduce a alkyne all the way down to an alkane. That'll be the first one we look at. Then we'll look at partial reductions, where we reduce it to a cisalkene or to a transalkene. Just as we saw with alkenes, hydrohalogenation of alkynes can occur in a Markovnikov or anti-Markovnikov fashion. The main difference is that since there are two pi bonds in alkynes, the addition can happen twice. Let's first look at Markovnikov addition, which is seen when dealing with a polar mechanism. Notice as we go through the mechanism that we'll be dealing with species that have plus and minus charges, and that's one of the indications that you're dealing with a polar mechanism. The mechanism that we're going to be learning about with alkynes parallels very nicely with the one that you already learned for the same reaction with alkenes. However, as we're going to see in just a few minutes, the current way of thinking is that the mechanism is actually a little more complicated than what we're going to see. However, what I'm going to show you is going to explain very nicely the outcome, and so if you memorize that, you'll be doing just fine. In the first step of the mechanism, the pi bond is going to come out, grab the H plus off of the HX, and the halogen will be kicked out as an anion. This gives us a carbocation, and what we're going to do is, let's go ahead and draw it, and we'll put the hydrogen there at the end, and then we'll put a carbocation, a charge, on the interior carbon. So we're going to put the plus on the secondary carbon because, just as we saw with alkenes, having the carbocation more substituted is going to be more stable. Then what happens is you have your halogen, your X minus, and then in a second step it comes in and attacks the carbocation, and you end up adding your first equivalent of HX across the double bond. This species is called a vinyl halide. And one of the interesting things to note is that the H and the X add trans to one another across that double bond, just as I've drawn there. Now, if you add a second equivalent of HX, what happens is the reaction, since you have another pi bond, goes again. And so the pi bond electrons come out, grab H. The halogen is kicked out as X minus, and again you'll have your original H, the second H that you added, and there's the halogen, the first one that I added, and the plus charge goes on the carbon that is already bearing a halogen. This has some real advantages because that plus charge can now be resonance stabilized. The halogen has lone pair electrons, and let's go ahead and we'll just draw them in. And those lone pair electrons can come down through resonance and help to stabilize the positive charge, and it gives the halogen a positive charge. So that helps to spread out that carbocation. And then you have your second X minus attacking the carbocation, and when all is said and done, you have created a molecule with two halogens on it, and both halogens are on the same carbon. They call this a geminal dihalide. That mechanism that we just saw serves very nicely to explain the regiochemistry and the gem dihalo outcome of that reaction. However, if you look at the reaction rates for the reaction, it turns out that the rate of the reaction is actually not in line with that mechanism. The rate is first order in the alkyne, but second order in the HX species. What that implies is that two equivalents of HX are in the rate determining step of that reaction, or in the first step. And if you look back at our mechanism, we have just one HX adding to make the first vinyl halide. So the mechanism needs a little bit of work. It turns out that the kind of accepted mechanism right now is one that actually avoids putting a plus charge on the double bond. So let's take a look at what they think is actually happening starting from that alkyne species. So there's our alkyne, and what we're going to do now is we're going to draw two equivalents of HX. And I'll put one on top and one on the bottom. And they suspect that what's going on is that the rate determining step actually involves reaction with both of those HX's at once. So where the halogen is adding to the pi bond, and pi electrons are going out and grabbing a hydrogen at the same time, kicking out a halogen, and you end up forming your vinyl halide. X is on the bottom, H is on the top, and there's the H that was there originally, and there's an X minus. You end up forming your vinyl halide that we showed in the earlier mechanism. But the interesting thing about this is this mechanism avoids an intermediate that we had drawn earlier. Remember this one with the plus charge on the double bond? It turns out that that particular intermediate is fairly unstable, and the mechanism involving the two molecules of HX in that rate determining step never has that carbocation on the double bond. In addition, the mechanism that we just looked at just now also helps explain that trans stereochemistry that is seen with this reaction. Now let's take a look at what happens when you do the reaction and your alkyne is an internal alkyne. The one we have been working with has been a terminal alkyne, meaning that the triple bond is at the end. But what if you have a triple bond and it is somewhere in the interior of the molecule? Well, things don't get quite as neat there. So let's go ahead, let's do this reaction with HBr. What happens is you end up with mixtures when you do this, because if you look at the carbons on that triple bond, they're both substituted the same. In our original mechanism, we knew where to put the plus charge because it went to the most substituted carbon. Well, that choice has been removed here, so it could go to either side, and it's going to be the same kind of a positive charge. So what that means is that you're going to end up with mixtures. So let's take a look, and we'll add two equivalents of HBr and take a look at the two things that could happen. You could have reaction on the side closest to the six-membered ring, and drawing that product, I had BR's across one side, H's across the other. I still end up with a geminal dihalide. You can see that right here. And the bromines still end up on the same carbon because the carbocation from the second addition is more stable, where it could be resonance stabilized by the first bromine. So you do end up with a gem dimethyl. But here's the complication. Everything that we just said would be true if you put the hydrogens on the first carbon and the bromines on the second. It'll still go gem dimethyl, but the bromines are now 2 carbons removed from that six-membered ring. So you can end up with mixtures pretty frequently. It's not a very clean reaction. The only time it would work out really nicely is if you had a triple bond and it was internal and substituted by the same things on both sides, so that where if you had substitution on both sides, it effectively wouldn't matter because it would be the same thing regardless. Now let's take a look at another hydrohalogenation, this time by a radical mechanism. What's going to happen here is very similar to what we saw with hydrohalogenation of an alkene under radical conditions. We're going to end up with regiochemistry that is anti-Markovnikov, and we'll also see that we end up with a geminal dihalide again. So you'll end up adding 2 halogens, but they're going to end up in an anti-Markovnikov fashion. So let's take a look at how that happens. We'll start out with what's underneath the arrow here. We see the HBr just like last time, but underneath the arrow now is the addition of peroxide. When this is exposed to light or to heat, so light will show by H nu, heat we can show by that triangle. So when you expose a peroxide to light or heat, you end up doing a homolytic cleavage and forming peroxide radicals. That's your initiation step, and you've now created a radical which can get the reaction going. So that radical then is going to react with the HBr, and the radical will come in with its 1 electron. The hydrogen and the hydrogen and the Br will homolytically cleave, and the net outcome of that process is you have, from the radical, you formed ROH, and you've created a bromine radical. So now the reaction is ready to go. It's that bromine radical that actually reacts with the triple bond, with the pi electrons in the triple bond. So let's see how it happens and why it is this reaction goes anti-Markovnikov. So here is our alkyne, and we're going to have that triple bond, the pi electrons, react with our bromine radical. What's going to happen is one of those pi bonds will homolytically cleave. An electron will go to a carbon of the triple bond, and an electron will go with the bromine radical. Now we have a choice as to where to put the bromine on the molecule and where to put the resultant radical. And let's go ahead, we'll put the bromine at the end, and you'll see why we make that choice in just a second. So the bromine's at the end, and the radical will go on the secondary carbon. This is giving us a more substituted radical, which is going to be more stable. So it makes sense that the bromine would go on the end so that the radical can be in the most stable possible position. And now we're ready for the next step in the reaction. And I'm going to have to try to squeeze in, I'll squeeze in my HBr over here. That radical that we just created on the alkene now is going to react with another HBr molecule, with the hydrogen specifically of it, and kick out a bromine radical. So we'll have a bromine radical, which then continues the propagation reaction, and we have our double bond, our H, our Br, and a hydrogen has been added to the molecule. And what happens is you now have a double bond, and that double bond can react with bromine radical again. And I'm going to go ahead and erase that. Let's just have that double bond reacting with bromine radical again. And when you repeat this process, you'll end up with hydrogens having added to the interior carbon, and you'll have your bromines at the end on the less substituted carbon. So you end up with a gem dihalide, geminal dihalide, and the regiochemistry is such that the bromines ended up at the less substituted carbon, and so you have anti-Markovnikov regiochemistry, an anti-Markovnikov reaction. And just as we saw with an internal alkyne in the polar mechanism that we studied last time, if the alkyne is internal, then you're going to end up with mixtures because you lose that selectivity of where it is that the radical would be most stable. You can see how that worked in this bottom reaction right here, where I have an internal alkyne substituted differently on each side. And when I do the radical HBr reaction, you end up with geminal dihalides, but they could be on one side on the triple bond, or they could be on the other carbon of the triple bond, and that does lead to different products. You could get away with it pretty neatly if your triple bond were substituted such that no matter what side it went to, you got the same product, but that was not the case here. So you do have to be a little careful with that reaction when your alkyne is internal. The halogenation reaction of an alkyne is very similar to the reaction that we saw with halogenation of an alkene. You can do halogenation with either Cl2 or Br2. And we'll go through and look at what the products are and talk about some stereochemistry, and then we'll show you the mechanism. So we'll go ahead and take this alkyne that's shown here, and let's go treat it with Cl2. And the first thing that will happen is that you will form a dihalo compound. And let's go ahead, we've got 5 carbons. And we're going to be just reacting with one of the pi bonds of the alkyne. So it will be an alkene, and we'll have 1 chlorine on one carbon and 1 chlorine on the other. So the chlorines end up at different carbons of what were the alkyne carbons, and they are adding in an anti-stereochemistry. So it's an anti-stereochemistry. And then when the reaction is done with the second equivalent of Cl2, again the chlorines span that remaining pi bond. It reacts with them, and you end up forming a molecule that has chlorines all over it. So you end up with 4 chlorines on it, or 4 bromines if you were using those. So let's go ahead and take a look at the mechanism and see exactly how that's occurring. In particular, the most interesting part is why this trans or anti-stereochemistry right there. The mechanism will explain that. So we will start out with, I'm going to redraw our alkyne here, and then we'll have chlorine bonded to chlorine. And we'll take one of the pi bonds, the electrons in a pi bond, and they will attack the chlorine, and we'll be kicking out a Cl minus. And what is going to occur, 1, 2, 4, 5, so we have a double bond, and we've added a chlorine, but just as we saw with an alkene when this occurred, the chlorine is actually going to span the 2 carbons in the former alkyne bond, those 2 carbons that are involved in that, and the chlorine gets a positive charge. And they call that a chloronium ion. If it were bromine, it would be a bromonium ion. So it's generically a halonium ion. Halonium, there we go. Halonium ion. And this helps to stabilize that positive charge and spreads it out over the chlorine and the 2 carbons. Forms a 3-membered ring. And then the other halogen is going to come and attack from the opposite side, and we'll pop that ring open. And that's how you end up with the anti-stereochemistry, because one halogen attacks that 3-membered ring from the opposite side. So your chlorines end up on opposite sides. You don't really need to talk about regiochemistry in terms of Markovnikov or anti-Markovnikov here, because the atoms that you're adding, the 2 chlorines here, are both the same. And so you don't need to talk about how one ends up more substituted than the other, because they're both the same. Then you do the reaction again with another molecule of Cl2, and this essentially becomes a chlorination of an alkene, following along with the same mechanism to put the 4 chlorines on. The next reaction we're going to look at is reduction of alkynes. And the first one that we'll see is hydrogenation, which is addition of hydrogen across the triple bond. We've already looked at this reaction with alkenes, and it's very, very similar when you apply it to alkynes, except for, as we've seen with the last couple of reactions, because you have 2 pi bonds, the reaction can continue to add once you get to the alkene and carry on, so you can have an alkene and then you can have an alkyne after that. So the first thing that we will do is we'll take a look at the reagents H2 and the metal catalyst. That you need the same sorts of reagents as we needed with an alkene. And as we learned with alkenes, when you have a metal catalyst, let's just draw it here sort of as a square, and we'll just say it's a nickel, make it a nickel catalyst. It reacts with the hydrogen, and you end up having hydrogen atoms sticking out of the metal catalyst, almost like a kind of a bed of nails, if you wanted to think of it like that. Then the alkyne comes down and settles down across this, and let's go ahead and we'll draw it like this. And the hydrogens can add to the pi bond system, and the hydrogens have to add from the same side. So they will add in a syn fashion. They come in from the same side because they're all sticking up out of that metal catalyst. And so what you end up with when you do your first addition is you end up with, let's draw the hydrogens in here. Let's actually sort of attach them, it would look better. Draw a hydrogen in right there and a hydrogen there. They're coming in from the same side. So you get a syn addition, and that results in a cis alkene. But as we saw, alkenes then react with hydrogen and the metal catalyst, go even further, and you end up at the end of that with an alkane. Now these conditions will of course reduce alkenes as well, and so let's say you had a molecule, let's kind of make one up here. Say you had a double bond in a ring, and then coming off of that you had a triple bond, and you exposed it to hydrogen, and let's just do platinum. So you have 2 things that will be reduced here. You have the double bond and the triple bond. And let's go ahead. Now with the double bond, we have this ring. We're going to have to pay attention to some stereochemistry, because those hydrogens are going to come in from the same side. So let's draw them coming in from the back side, and that's going to push that alkyl substituent up. So the hydrogens come in from the same side on the double bond, and we have 3 carbons. 3 carbons on my substituent, and the triple bond will be fully reduced. And so we're not going to have to worry about any type of stereochemistry there. As we saw in the last reaction, reduction with H2 of an alkyne, the alkyne passes through a cis alkene and then is further reduced to form an alkane. Often you would like it to stop at the alkene stage, because then you retain that functional group, which you could then turn into a bromine or an alcohol or any number of things. Alkenes are fairly useful. Let's talk first about what not to do when you're trying to get the reaction to stop at the alkene stage. So let's put don't. You don't want to try to limit the amount of hydrogen gas. It would be tempting to say, oh, if I just want it to add once, I'm just going to add 1 equivalent. But what happens is the alkene reacts faster than the alkyne, and so you'll end up forming some alkene and that alkene will react quickly to form alkane, and you will very quickly end up with a mess. So let's list what you will get. You will have alkane from the alkene reacting. You will have alkene, and you will have some alkyne because you will have run out of H2. So we don't want to approach it that way at all. What you do instead is you change your catalyst. We're going to be using, to accomplish this, something called a poisoned catalyst. And there are two common ones that you may run into. The first one is the most common, and that one is a catalyst that is called Lindlar's catalyst. And it's palladium, and it has been treated with barium sulfate, methanol, and quinoline. Another thing that you may see occasionally is nickel boride, Ni2B. That's also a poison catalyst. And what these catalysts do is they won't reduce alkenes. And so your reaction goes to the alkene, and the catalyst is not capable of reducing the alkene, so the reaction stops. And that's a very clean, very neat way of stopping, is you just choose a catalyst that forces you to stop. And so you can see that in this reaction that's written up here, you have a triple bond. It reacts with H2. You end up forming a cis alkene, and because the catalyst is poisoned, it can go no further. And the stereochemistry is, of course, a syn addition, because it's still the hydrogen. There's the metal, just that the metal has been, if you want to think of it this way, it's been deactivated. So that's a great way of forming a cis alkene. There is another thing that you can do, and that will be on the next slide, and that's for forming a trans alkene, should you decide that the stereochemistry needs to be trans. The third reduction that we're going to examine is a reduction of an alkyne, and it will create a trans alkene. And again, as we saw with the poison catalyst, it will stop at this stage, and it will react no further. So it's a way of forming an alkene, but with a trans or an anti-stereochemistry. This reaction is sometimes called the dissolving metal reduction, and the reason for that has to do with the reagents that carry it out. In this reaction, you take sodium or lithium metal, so that's where the metal part of dissolving metal comes, and you essentially dissolve the metal in liquid ammonia. What this does is it creates an electron, a lone electron in the solution, because sodium and lithium like to lose electrons, and so they do. They lose an electron, and so this mechanism is actually not too complicated, but it's not important to go over its mechanism, but it involves radicals, and so it is going to be a radical type mechanism. And what happens in this mechanism is the alkyne gets reduced to an alkene, but alkenes don't react with it. And so the mechanism stops once the transalkene has been achieved. The key intermediate in the reaction that gives the trans stereochemistry is the following radical. I'm just going to use R groups to signify the alkyl groups that are attached. Once that triple bond has had an electron added to it, and it picks up a hydrogen from the ammonia solvent, so So it's had an electron, it picks up the hydrogen, and there's our radical. That's the key radical. This is most stable, this radical, in the trans stereochemistry because it gets the R groups as far apart as possible. And so you get to that radical, it will exist in the trans stereochemistry, and then as the reaction goes further along, what that ends up doing is it ends up getting those R groups trans to each other. And so that's why you have that trans stereochemistry, is because of that radical stability. So that's another way of doing a reduction. So now you have three. You can reduce all the way with hydrogen and a metal. You can stop at the cis-alkene with hydrogen and a poisoned metal catalyst. And you can stop at a trans-alkene with the dissolving metal reduction, which is sodium or lithium in liquid ammonia.